Good afternoon, everyone from Lausanne, SICAM headquarters here. My name is Sara Bonella. I am the Deputy Director here at SICAM, for those of you who have never met me. And it is my pleasure to welcome you to this new session of the Mixed Gen series that we've inaugurated a couple of years ago in more complicated times for traveling, when SICAM prevented in-person exchanges between younger members of the community and us. And so we thought about creating this venue for providing an opportunity for exchange and also for visibility of the research of our younger colleagues. This was met with good success. We received many positive comments from you, and so we've decided to keep going with this type of event, fully online, and covering a very broad range of topics. Today, we are going to discuss simulation and modeling of non-equilibrium phenomena, and it is my pleasure to welcome our experienced, I can't bring myself to say senior speaker, Deborah Bernard from the University of Queensland. Her talk will last about an hour and discuss non-equilibrium molecular simulations, predicting results where theories do not exist. This will be followed by two shorter talks, about 20 minutes each, from Benjamin Sorkin, Tel Aviv University, on universal relation between entropy and kinetics, and a talk from Pasquale Di Gregorio from the University of Barcelona, active turbulence and topological defects in nematic liquid crystals. These sessions are recorded. You will find them published both on our YouTube channel and on the SICAM webpage corresponding to this session. So, you're welcome also to mention that we've had these events to colleagues who could not attend, should they be curious to listen in. The protocol is the usual one for online Zoom type of webinars. We ask you to refrain from asking general questions until the end of all talks. But if you have a specific question during Deborah's talk, something very technical related to, I don't know, maybe an equation on a slide or something, just type that question in the Q&A session and I will relay it to Deborah. For the longer questions at the end of each one of the presentations, just signal in the Q&A that you want to ask the question, and then you will be invited to unmute yourselves and to turn on your camera, and you will have an opportunity to ask the question directly to our speakers. This is only possible on invitation. Any other mode of communication among remote participants and you and the speakers is turned off right now. So I will be your interpreter and translator through the Q&A for anything that goes beyond the questions. Okay, that said, without further ado, Deborah, the stage is yours.
Thank you very much, Sarah. Thank you for your kind invitation to speak here and also your introduction. So let me share my screen. Okay, can you see that okay?
Yes, it's fine. Thank you.
Oh, let me go back. Okay, I know I just need to get this out the road so I can see it as well. Great. So yeah, no, it's a real pleasure to be invited to speak at this forum, and I think it's really a wonderful idea. I've really enjoyed listening to the talks that have been recorded and learnt lots of things, and makes it easier when you're not in the same time zone, if you can do that. I'm going to talk very generally about non-equilibrium molecular simulation, at least at the beginning, and give a bit of a background, because I understand that there's a mixed audience, and hopefully touch on some of the traps that you can fall into if you're carrying out non-equilibrium molecular simulations yourselves. And in the second part of the talk, I'm going to talk a little bit more about developing theories when they don't exist. Most of these will be things which have been around for a while now, just a few new results. And hopefully there'll be something there for everybody. Before I go into the talk, I just want to acknowledge a number of people. First of all, my current group members, some of the work that they've been doing will be presented today, but other people are working on quite different projects. But also the contributors to my work that I collaborate with or have been in my group in the past. And there's quite a long list of these people that have really been involved in the development of theory and methodology for non-equilibrium simulations that I'll be presenting. But I should also note that this talk is largely an overview and includes research which has been done by many people not included on this list. And I would like to recognise their work as well, and I'll add a few references, but recognise that some of this work has been established over a long period of time. Finally, I should acknowledge the people who have supported the work, the Australian government through the Australian Research Council over a long period of time, the NCI in Canberra, which is our national computational facility, the Pawsey Centre, which is another major computational facility in Western Australia, and our local research computing centre. So before we get into it, I need to define what I'm talking about when I talk about non-equilibrium systems, because I think there's very many different interpretations of this. And so what I really think of when I think of non-equilibrium systems is anything we see around us. An equilibrium system is somehow an idealized state. And there's a lot of theory and thermodynamics, statistical mechanics developed for equilibrium systems, but it is quite an idealized system. And everything else, everything we really see is in a non-equilibrium state to some degree. Very many of the systems we see around them, or parts of the system we see around us, are very well approximated as an equilibrium system, and therefore thermodynamics and statistical mechanics of equilibrium system is obviously an extremely important area. So the systems I show here, just photographs of different systems, are all non-equilibrium systems, and I would say that these are substantially non-equilibrium. A lot of them, if you look at the water boiling koala, something which is living, paint being mixed down here, and other fluids undergoing different flow, and a chemical reaction, flame burning up here. They're things where if we looked at them a little later, they'd look different, so they're evolving with time. But these two here, this is a hot water tap with some lights glowing, and some water being driven by pressure and streaming down here under gravity. These systems will look pretty much the same because they're in a steady sort of state. But in both these cases, they're being driven, and this one's got the power here is being, the light here is being powered by electricity, and we're getting some dissipation of heat. Here we've got the water being pushed by a pressure and also by falling by gravity. And so these are subject to some forcings, and we're getting some fluxes occurring in these systems. So they're both non-equilibrium systems as well. One system which I won't be talking a lot about today, but often people think of when we think of non-equilibrium systems, especially if you're outside the modeling area, or even in the quantum chemical area, is that they're systems which are not in their global lowest free energy state. So they might be trapped in a local minimum. And so I tend to refer to these as quasi-equilibrium. The statistical mechanics of these systems will be well described by equilibrium statistical mechanics. And the reference down here was some work by Stephen Williams and Dennis Evans in collaboration with me, where we looked at how, if you had a system with a double well, you can say that definitely one of the wells, if the particles are trapped in, the system is trapped in one of the wells, then it satisfies the Boltzmann distribution in that case. Another way of classifying non-equilibrium systems is to describe them as transient, steady state, or relaxing systems. So if we have a look at our paint, which has got yellow and red paint being mixed, we could say that as it's being mixed, it's undergoing a relaxation to a steady state. It'll still be in a steady state because the stirrer might be still going, but its properties will no longer change. So we have the transient where the properties change with time, the steady state when it doesn't change with time. And we would describe this as a system which was relaxing towards a steady state. We could also have a system, if it wasn't being stirred, if we stopped stirring it, then relax towards equilibrium. So by steady state, I will be referring to a non-equilibrium steady state, and I'll just refer to an equilibrium state as equilibrium. We can also classify the non-equilibrium systems by the way that they're being driven. So we can have systems which are boundary driven. In this case, it would be boundary driven. The flow of the paint is being driven by the axle here. And the boundaries are then used to produce a non-equilibrium state. And we can also have systems which are field driven, like a charged particles being driven by an electric field. I'll also mention some cases where we use fields to mimic the effects of boundary-driven flow. And so there's a field-driven flow, which is just mimicking the real boundary driving. And that's also an important area. So this is a system, a non-equilibrium system, where we've got polymers aligned initially with the walls, and we're moving this bottom wall to the right. The little blue particles are just tagged particles so that we can see the flow, and the top wall is moving to the left. So if I play that, it starts off in one state, it's evolving. There's a thermostat being applied to the walls, so the shearing that's occurring due to the moving of the walls is heating the system up, but the energy is being extracted through the thermostat. And so we have a system then which reaches a non-equilibrium steady state, which is continuing to be driven. This is a boundary-driven simulation, and we'll see how we could convert that into a field-driven simulation. Also, I want to distinguish between homogeneous and inhomogeneous systems. We can have inhomogeneous driving forces. Most of the large-scale systems that we looked at in the first pictures were systems where part of the system was being driven and not all of it. And again, we can have thermostats which are acting locally or globally. And we can think of a water bath, for example, where part of the system's being heated or cooled. And we could think of also a microwave where the system is being heated throughout. So we can have different ways of controlling the temperature. Okay. So some of the types of systems that we typically study using simulation, which are in non-equilibrium states, are systems, say, with a density gradient, systems which are being driven by a field. So we could have charged particles being driven by an electric field. We could have magnetic particles being driven by a magnetic field. We can have systems which are undergoing flow, like the system we have here, which are being driven by walls or in some other way we'll describe. And we could have temperature gradients. So we can have different gradients. So there's a whole range of different properties and combinations of these that we might want to simulate. In the talk today, I'm going to be focusing on particular classes of systems. We're going to be looking at many particle systems, interacting particles. We're going to model these systems at the atomic or united atom, or maybe even molecular level. The dynamics that we use to model them is deterministic dynamics. I'm going to be talking solely about deterministic dynamics today. The equations of motion will be classical, and we'll be sticking, when we talk about flow, to laminar flow, so avoiding turbulent flow, which is actually relatively easy in the small systems that we tend to look at. Okay, so just some terminology so that you can follow what I'm talking about, particularly in the latter part of the talk. I use capital gamma to represent a point in phase space. So that's the positions and the momentum of all the n particles. So here we have a 5-particle system. It's got positions and the vectors representing their momentum. We have a point in phase space, and because our dynamics is deterministic, it will follow a trajectory, connected trajectory, as we move through the phase space. We talk about an ensemble of points. I'll use f of gamma to represent the phase space distribution function, and the probability of observing then some points within a small phase volume d gamma will be given by the phase space distribution function multiplied by d gamma. Okay. We'll also use the ergodic hypothesis in some places. And basically what we mean by this is that even if the system isn't truly ergodic, the phase space averages will be equal to time average if the ergodic hypothesis is satisfied. And again, you can see the types of notation I'll be using here. So the average, the ensemble average value of the energy is given by the integral over all phase space of the distribution function and the energy, of course. And if the system is ergodic, we'll have some dynamics which will sample this distribution F, and therefore the time average of the property will be give the same value. So this assumes that the distribution function actually does exist, and there's the dynamics that will generate that distribution function. I'll use B to represent just a general phase variable. So that could be the pressure, it could be the temperature, it could be the energy, but it's something which just depends on the position in phase space. Okay, so before I talk about non-equilibrium systems, I'd like to just mention a few things about equilibrium systems, which are also relevant when we move to non-equilibrium cases, but also point out some of the important things which differ in equilibrium and non-equilibrium systems. So the classical equations of motion can be solved to model a system at equilibrium. So they're just Newtonian equations, and they're obviously very simple. But to solve them is not so simple. The reason why it's not so simple is that the equations are coupled. The force here depends on all the positions of all the particles in theory, although we will usually cut off beyond a certain cutoff radius in a molecular dynamics simulation. So that's one challenge. You can't solve the equations analytically. You need accurate values of the forces. I'm not going to touch on that at all today, but that's obviously really important if we want to model a system. And another factor is that we would like to usually simulate large systems for long times. And despite the simplicity of the equations, we can model very complex systems. And this is some work that Mirella was doing in my group, looking at a reverse micelle. So obviously a very fairly complicated system. In this case, actually, we could model the whole micelle, and it would be doable using normal sorts of computing systems. So in this case, the system is sort of a nanoscale size, but we would usually like to model even larger systems. And by large, I mean bigger than microns, and like to look at them for long times, by long meaning longer than microseconds, perhaps approaching milliseconds these days. So these are big challenges and already makes it modeling accurately large systems complicated. So how do we address the system size? So in some cases, as in the micelle case, we can, our system is actually nanoscale. Otherwise, we may have real boundaries that we can impose, which are good, or perhaps we can have systems with boundaries, which is very large. But the boundary effects, as you can see in this simulation, and looking at the structures that we see here, the boundary effects are quite significant, at least on the scale of this butane in a nanotube. And so that's something that we need to consider carefully. If we want to model a system which is larger than nanoscale, we need to start to use periodic boundary conditions. And periodic boundary conditions mean that we can model just a small number of particles, but allow it to represent a bulk system. And again, we need to be quite careful in the choice of boundary conditions. If it's a fluid, it's quite straightforward. We can just have cubic boundary conditions. But if we've got a system which has some solid phases in it, it's important to ensure that the boundary conditions are commensurate with the unit cell of the solid that we're looking at. So the size of the system then is limited by the inhomogeneities in the system. And also, if there's some hydrodynamic behavior, we need to make sure that the system is larger enough to allow that to be properly accounted for. Okay. So the classical equations of motion, Newtonian equations of motion that we would use to model an equilibrium system, will sample the microcanonical ensemble. And this has been well known for a very long time. But I'd point you to a paper perspective article recently where we show a way of, or outline or summarize a way of deriving the ensemble that's sampled by a set of dynamics by ensuring that the distribution function doesn't change with time at a fixed point gamma. And this is something which has been developed, and we just show it for a number of examples where you can have some dynamics which generates different ensembles, and other cases where you can't find a distribution function which will be preserved by the set of dynamics. But often we're not interested in systems which are completely isolated. These assume that there's no thermal or mass transport across the boundaries of the system, and therefore we would like to model a system in contact with a thermostat, and therefore one way of doing that is to modify the equations of motion to incorporate a thermostating term. There are many types of thermostating methods that can be used, and typically in our work we would use either a Gaussian thermostat, which fixes the kinetic energy of the system exactly, or an Ose-Hoover thermostat. So the Gaussian thermostat will sample the canonical ensemble with a delta function on the temperature, on the kinetic energy, and the Ose-Hoover thermostat would sample the canonical ensemble with an additional degree of freedom, the thermostat multiplier, which is Gaussian. So there are other choices that can be made. The reason we usually stick with Gaussian and Ose-Hoover thermostats is that they're both deterministic, they're both time reversible, and that will be key to some of the derivations that we're interested in doing later. Okay. So often, in both those cases, Gaussian and Ose-Hoover thermostats, the equations of motion are adjusted by adding this additional term. And it's very important, and this was one of the traps that I wanted to point out, it's very important that we do this thermostating with respect to the frame of reference where the total momentum is 0. If we have a system where the system is moving, for example, the streaming velocity, in this case the ice cube moving up, will be the energy, or the kinetic energy associated with that, will be interpreted as thermal energy, and the temperature, the apparent temperature, would be much too high. So normally we would set the total momentum of the system to be 0. So we're in the frame of reference of the center of this ice cube. And then the change in the position will be equal to the momentum on the mass, where this momentum is just the thermal momentum and has no streaming component. So it's important that this thermostating term works on the thermal momentum and not the it doesn't include a component due to the streaming. And that will come up a little bit more when we talk about non-equilibrium systems. We can thermostat not all the system, but just part of the system by just introducing a switch. So for the micelle system, we might just want to thermostat the organic region and allow the aqueous region to be able to be evolving under Newtonian equations of motion. To ensure that the total momentum is conserved, we will, or zero is not just conserved, but zero, we will subtract this streaming component of the subset of particles from the total. Okay, so we can model equilibrium systems, and we've got the phase space distribution function, and therefore we can calculate phase variables using Monte Carlo methods, or we can use molecular dynamic simulations. We know relationships between the different thermodynamic properties, and we know that the change in free energy as we move from one equilibrium system to another should be negative. We can also calculate transport properties like the diffusion coefficient, thermal conductivity, and the viscosity from the fluctuations in the system through a molecular dynamic simulation. So we can get a lot of information about these equilibrium systems. So now let's move on to non-equilibrium systems and see where they differ and where they match. So the same issues exist, of course, in non-equilibrium systems, but there's a few more challenges. One of the challenges is that the boundaries that we were talking about, the periodic boundaries, might change with time. Another issue is that there will be different kinetic temperatures in different regions. So we don't have thermal equilibrium in a non-equilibrium situation necessarily. Could be time variation in the forcings that are being applied. We don't know the phase space distribution function, and there's not a lot of thermodynamic relations known for non-equilibrium systems. And I think we'll hear about some of these issues also in a later talk. So looking at the challenges, one might think, okay, let's give up, but there are various ways we can overcome these challenges. So often we can assume local thermodynamic equilibrium. So we might just model part of the system, say this was a Newtonian fluid, we might just model the yellow region and assume that that's at equilibrium. We can use linear response theory. So if we've got fluxes which are proportional to the field which are being applied, we can predict what those fluxes will be. We can do direct simulations, or we can develop some new theory. So the two things I'm going to focus on are direct simulations and then the development of new theory. Okay, so first of all, direct simulations. How do we know how to simulate equilibrium systems? How do we change it to simulate non-equilibrium systems? And so using this deterministic approach, what we can do is just change these equations of motion by adding some coupling with various fields through some matrices CD here, and choose this coupling in order to model the system that we're looking at. We don't have to use the same equations of motion for all the particles in the system. We can use one set of equations for part of the system and another, just like we only thermostated the part of the system. And therefore we can introduce control volumes. We can have non-physical regions to represent the boundaries of these systems more realistically. And we can also have systems where we drive the system through the walls like we saw in the simulation previously. So just looking at that a little bit more closely, the equations of motion for the particles in this system, which was undergoing shear flow, are given here, where we're got the change in the positions of the particles on the top wall. Are there due to their thermal velocity plus or minus the streaming velocity in this case. So it's moving backwards. And the bottom wall is the same, except we're adding a streaming velocity here. We've also got the fluid particles, and in this case, they're just being treated as Newtonian particles. Also, the thermostat's just applied to the wall particles in this case. And so we can model this system in this way. And by thermostating the walls rather than the fluid, we might, for particular systems, make it more realistic, I guess. Also, we're not adding any sort of fictitious fields to the particles which are flowing. So this is trying to mimic the system as well as would occur in nature. So this could be for studying lubrication between in a very narrow nanopore. Lots of different sorts of systems we can model. This was a system where we were looking at supercapacitors and trying to determine the spacing between, or spacing of the pores in order to get the ionic liquid to insert, looking at these melting and solidification of water. This was an example where we were driving some molecules into a micelle to allow it to swell for drug delivery. And so there are lots of different systems that we can model by changing the equations of motion, but basically fairly straightforward equations of motion. But we mentioned with the equilibrium systems that the boundary conditions were important. We had to be commensurate with our problem. And also we mentioned the issue of thermostating. So I just wanted to touch on these two issues and how they are different and even more complicated in non-equilibrium systems. Okay, so in the top, we've got our boundary-driven shear flow, where we've got our fluid between the walls, which are moving in opposite directions, and we'll get a somewhat linear velocity profile across this slit. Because of the interactions between the walls, it won't be completely linear. There'll probably be either some slip or stick with the walls, and that will change that profile here. The density near the walls will be higher, and so it won't be completely linear. If we were trying to model a real, well, not a real, but a larger system, these wall effects would be problematic, and we should try to change how we would model that. We would like to model it as a bulk system, essentially, but with a linear velocity profile. And the equations of motion that have been developed long ago, Dennis Evans and Bill Hoover and their groups were heavily involved in this, are what we call the slot equations of motion. It's one way of doing it, and the way I would normally do this. The slot equations of motion have our normal Newtonian equations of motion, but you've got a term here which is related to the gradient of the velocity profile, and also another term in here. So these are general, and this gradient of the velocity profile can be adjusted to whatever type of flow that you want. So these slot equations of motion can measure model planar shear flow, wet flow. It can model expansional flow that you can see on the right-hand side here. It can model rotational flow and elongational flow by adjusting what this gradient of the velocity profile will be. And you can see that these simulations for the rotational flow, elongational flow, and shear flow can go on forever, essentially. They're periodic, the boxes are periodic in time, and the density of the fluid doesn't change. So we can reach a steady state in those systems. In the expansional flow, the difference between these is this one on the right is being modeled with slot equations and the box growing, whereas the one on the left is just the box is growing with time, and you don't have any forcing on the particles. And so there, the velocity profile is not as uniform as it is on the right-hand side. But in both those cases, clearly, these have just been played in loop, and therefore they're not going to reach a steady state. They're forever expanding. We could have a system which expanded and contracted and model that as well. So this is a way of, when I was talking about converting the boundary-driven flow into a field-driven flow, these terms here are acting like a field on the system, which ensures that the correct flow profile is created. Now about thermostating, and we need to be a little bit careful here as well. So here we've got just the planar Couette flow occurring, so it's shear flow. And so our velocity of this particle has a streaming component moving across. This particle's at y = 0, so it won't have a streaming component. And if we had a particle down here, it would be moving to the left with that streaming velocity. And the equations of motion for the Couette flow and a shear flow are given here, and this is the gradient of u. And that's fine. If we look here, this particle, if we focus on this center particle here, we can see it has no streaming component, and that's represented here, that the value of the y is 0, and therefore this term will be 0. All the velocity would be associated with thermal energy. And so our thermostat is acting on this momentum, which is just the thermal contribution to the momentum. And that's fine. But there will be a rotation occurring on this particle, being forced to be rotated. And in this case, that doesn't matter because this rotational motion isn't being modeled by these equations of motion. But if we had a particle, which was a molecule composed of atoms, for example, and this same rotational motion would be exerted on this particle, there's a problem. So how would we model this? How would we change the equations of motion to look at a system composed of atoms? And the natural thing would be to replace all these i's, which represent the particle or the molecule, with an I alpha to represent the alpha atom of the ith molecule. And so just replacing all of that throughout here. But let's look what happens with this thermostating term now. If we look at this atom here, which is at y0, it will have, according to this term here, this is only in the x direction. There's no component of the streaming velocity in the slot equations of motion associated with the y direction. And therefore, the momentum here of this particle will be both the streaming due to the rotational motion of the molecule and the thermal part will be contained in this momentum, which is represented here, which is the one that we're thermostating. So in this case, the temperature would appear larger than it was because of this rotation. The thermostat would be extracting that energy and it would impose a torque on the system, which would prevent that rotation. And this issue has been known for a very long time, and an easy solution to it is to apply the thermostat just to the center of mass of the molecule. If you want to go to higher strain rates, having a look at longer chains, then there's more sophisticated ways of doing this and would be necessary. But even in the linear regime, if we apply an atomic thermostat, we will end up with incorrect behavior. So as I said, these sorts of simulations have been around for a long time. There's early work on simulation of the rheology of N-alkynes in 1987, and that was considering the correct treatment of the rotational motion or of the molecule and the thermostating, and looking at more sophisticated ways as time goes on. I should also note that the boundary conditions that have been developed for a long time. So the first system to be able to be modeled using undergoing homogeneous shear flow is the Couette flow. And that was using Lees Edwards boundary conditions. So that's really 1972, dated from 1972. But there's still work being done in developing boundary conditions for different flows. And this paper by Matthew Dobson is published earlier this year. And Thomas Hunt's also been doing a lot of good work in that area. So these boundary conditions for a planar shear flow have been around for quite a long time, but good ways of treating the boundary conditions to create homogeneous flow for some of the other types of flow are relatively new. Okay, so that was work which had been developed, and we use these methods regularly. And in the past, we were mostly interested in applying these sorts of models to fairly simple systems. So we had our own code, which we were confident in, and which were slow though. And so we could only model fairly small systems. We're interested in applying shear flow and looking at flow in larger systems. And so rather than using or developing new code to create very complicated system, we thought it was the best idea to use code which is existing and which these types of algorithms are just starting to be developed in. Unfortunately, a lot of them are developed for using atomic thermostats, and also are not optimized for looking at large systems with varying boundary conditions, time-evolving boundary conditions with charged particles. And so what we've been doing is trying to build into some of the codes which are readily available, efficient and accurate ways of modeling this type of behavior. One other thing that I didn't mention, but which is really important, is that the development of non-equilibrium simulation algorithms in the early days was partly done not just to simulate systems which are out of equilibrium, but also to calculate the linear transport coefficients. And so if we can develop equations of motion which result in a flux which is associated with particular transport coefficients. So for example, if we were looking at the thermal conductivity, if we could develop some equations of motion which had produced a heat flux, and we knew what the temperature gradient was, we could calculate the linear transport coefficients. And so a lot of the initial algorithms were developed in order to calculate the viscosity, the diffusion coefficient, the conductivity, and the thermal conductivity. And I'll come back to that a little later, but this is a good way of calculating these transport coefficients when the correlation times are long. So Green-Kubo relationships, which are what are used, or Einstein relationships, which are what are used in equilibrium simulations, don't converge in a sufficiently short time. And they've been successful in that regard. If you wanted to look more on the the sorts of algorithms, the equations of motion that have been developed, these two books are excellent resources. Okay, so I want to stop there talking about the direct simulation. So that's how we would model non-equilibrium systems, and just hopefully pointing out some of the traps that you can get into, particularly having systems where the total momentum is not zero, having systems where the thermostating's done incorrectly, or having systems where the boundary conditions need to be modeled properly in order to get continual flow occurring. So what I wanted to do now is to start talking about some new theories, or another approach where we can develop new theories to try to understand the non-equilibrium systems. So in equilibrium systems, one of the important factors is that we can calculate whether a process will occur or not, if it will move from one equilibrium state to another by looking at the change in the free energy. And so what would be good, or what is good, is that we can do the same sort of thing for non-equilibrium systems. So this is work which has been around for quite a long time now, but I thought it might be useful to go through how we approach deriving fluctuation theorems, which are essentially a way of predicting whether a process will occur in one direction or another. From the fluctuation theorems, we can derive dissipation theorems for nonlinear response. And then from that, we can get back to the linear transport coefficients, which is what we measure at equilibrium. So let me just go through just describing how you can derive an equivalent relationship for a direction of a process where we're in a non-equilibrium state rather than an equilibrium state. Okay, so this image here is representing, say, a polymer. Maybe they've got charges on either end. We apply a field and the polymers stretch out. And so we have an initial state which is at equilibrium, and we apply a field and we observe the polymers responding to that field. If our equations of motion are reversible, or there is a time reversal, where there is a mapping which will allow us to produce the reverse trajectory, then if we start from this configuration, which is a time reversal map of this one, that is, the positions are all the same, but in this case, with just a field-driven flow, the momentum changes. Then we solve the equations of motion, we'll end up, if the dynamics is time reversible, back at the same configuration, but the momentum is also in the reverse direction. And so what we might want to ask is, what's the likelihood of going from this entangled polymer to this stretched polymer under the influence of a field, compared to the probability that the reverse process would occur? And this is what fluctuation relations are all about, looking at the probability of a forward and a reverse process occurring. In order to develop a relationship for that, look at the figure on the right-hand side where we have a point gamma. We evolve it in time along this trajectory to a point gamma at time t. And if we do a time reversal, we map to gamma star, we evolve to gamma star at t, just like in the image on the left. But instead here, let's consider a small phase volume about these points and look how that phase volume will change as well. So we have sets of points within this phase volume, they'll all evolve, and because of the deterministic nature of this process, they'll all be in the vicinity of that initial point at the end, but the phase volume may have contracted or expanded. The probability of observing this set of trajectories compared to that set of trajectories is given by the relationships down here. So the probability that we evolve from this region to this region compared to this region is given by this. Because it's deterministic, the probability of observing this set of trajectories will be just given by the probability of observing the initial set of points, and the same on the denominator. And if we know what the phase space distribution function is initially, here we've got the phase space distribution about gamma at time 0, we can write the probabilities in terms of this distribution function. And at this point, we define this ratio, this probability ratio, by this term here, and we'll see why a little later. So this is still arbitrarily general. We've got this ratio will be non-zero and positive, and just as this exponential term will be. So this is quite general. This is a function of the dynamics. This is also a function of the dynamics because the change in this phase volume as it evolves along here will be a function of the dynamics. And so we can write this probability ratio then, and I'm going to introduce the terminology. Omega subscript t is just the time integral of omega along that trajectory. Because of the deterministic nature of the system and this, the symmetry with respect to time reversal, we have what we call the dissipation function along this trajectory will have an equal and opposite sign, will be equal and have opposite sign to the dissipation along the conjugate trajectory. If we take all the set of trajectories for which the value of this dissipation function has a value A, we can look at the probability that the dissipation function integrated along time t will take on a value A. And so we can just integrate over all the points where this condition is satisfied. And substituting for f gamma d gamma here, we can obtain, after a few steps of algebra, a relationship which says that the probability that the dissipation function average integrated along trajectory t has a value A is equal to the exponential of A times the probability that the value of the dissipation function along the trajectory will take on a value minus A. And so just rearranging that, we can derive then this relationship, which is a fluctuation relationship. We call it a transient fluctuation relation because it depends, or it involves this initial distribution, which we must know because it comes into the definition of omega. From this, it's straightforward to work out what the average value of omega would be. And we find that it will be positive or equal to zero, but it's only equal to zero if there's no driving force. So if we're at equilibrium, essentially. So this relationship then is a second law-like relationship, but applies to a non-equilibrium system and gives you the probability of observing positive and negative dissipation. Okay, so we introduced the omega value, but what does it mean physically? So it is the log of the probability ratio of observing those trajectories. It's uniquely determined by the initial distribution and the dynamics. But what does it actually mean? If we determine what it would be for a system where we've just got a thermostated system initially at equilibrium, and then you apply a constant field, which could be a field which is mimicking a boundary-driven flow, like a strain rate, or it could be something like an electric field. We find that the dissipation function is just equal to the 1 on kBt, the volume of the system, the dissipation that's occurring, and the field. So this could be an electric field, and this could be an ionic current, flux. This could be a shear stress, and this could be a strain rate. And so this then says that if we substitute into the relationship which gives the sign of the value, it will say that the flux must be greater than or equal to zero for these systems. So this is what it is for a system where we've applied a constant field, but you can also treat systems where, say, you change the temperature of the system, or if you do other perturbations to the system to drive them away from equilibrium. So it's quite a general relationship, provided you know initial distribution and the dynamics. Okay, So this was a transient relationship. We started at equilibrium. We looked at the probability that the dissipation took on a value of A or minus A, and we found the relationship. But we can also look at steady state trajectory segments where we look at the average value of the dissipation along a trajectory of length t and take the probability ratio, take the logarithm 1 on t, and this will be equal to A. So we can get a steady state version of that fluctuation theorem. And if you wanted to know a little bit more about how you get from here to here, probably the best reference would be the first one given here. In recent work, we've extended this. So this is the transient relationship is true at all times or for all trajectory segment lengths, whereas the steady state relationship's only true when you have long trajectory segments, so in the limit of long t. So what Stephen Sanderson in my group has been doing recently has been using machine learning to develop a steady state relationship for deterministic reversible dynamics, where we determine what the function would be in order that the steady state relationship would be obeyed. And that work will be available very soon. Okay, so how am I going with time? Probably a little slower than I would have liked. So I might just go quite quickly through this next section. Once we've got the dissipation theorems, we can derive other relationships from them. And one of the relationships we can derive is the dissipation theorem for nonlinear response. So it's an expression for the nonlinear response of a system. Okay, so I won't go through this slide and never intended to go through this slide in detail because it's quite full. But what we can do is using our definition for the dissipation function or the time integral of the dissipation function that we were talking about earlier, using the fact that the number of points within this phase volume doesn't change along this trajectory. So this is like a Lagrangian form of like a Liouville equation. We can combine these relationships to see how the phase space density of a particular point will change with time as the system evolves from a known equilibrium state towards steady state. So importantly, we're going towards a steady state. So there still is a distribution function that will describe it. The system doesn't become of a lower dimension, doesn't collapse onto a lower dimensional space. Using that and our definition for the time evolution of a phase variable in terms of the value of the phase variable at a point gamma and the time evolved distribution function, we can substitute in these relationships and obtain a relationship which we refer to as the dissipation theorem, which is given here. So that's going really quickly through this, but really we're not using anything extra rather than this definition of the dissipation function to what would be already known. And then it's just algebra, and you can derive this relationship which tells you how the phase variable B will vary with time. And it's related to this time integral of this correlation function between the dissipation function and the property that we're interested in. Again, this is very flexible. So this could be the response to a change in temperature. It could be the response to the application of a field. It could be the response to a flow. So this also looks at any phase variable that we would like to look at. If we had our system where we had a field-driven flow, we can substitute into this general expression the dissipation theorem for that particular system. And we could also choose our phase variable to be the flux. And if the phase variable is the flux and the dissipation function is given by this, which has the flux in it, we'll end up with the flux equal to beta V Fe, and we'll have this correlation, autocorrelation between the flux at time 0, the flux at time s, and we take the integral of that to determine what the flux would be at time t. So this is an interesting result, and it's known as the transient time correlation expression for a phase variable, which has been around for a while for systems where of this kind, where we've got a homogeneous field and we're just applying this to a system and homogeneously thermostating it. This generalizes this expression in terms of the dissipation function, generalizes that expression. It's interesting because you would think it's much more simple to evaluate the value of the phase variable directly by doing this ensemble average, rather than doing the correlation function and taking the ensemble average, which seems much more complicated. But it turns out that the statistics of the numerical evaluation on the right-hand side gives results which are statistically more precise than if you evaluate the left-hand side. Also, if we take the linear regime, so if we have low fields, this correlation function here, which would be evaluated with the field applied, will be to first approximation or to 0 order in the field, will be just the equilibrium correlation function. So this then is the linear response expression if we take low fields. We can divide the flux by the field, and then we can calculate the transport coefficients. And so this becomes then like a Green-Kubo relationship for the transport coefficients at equilibrium related to the non-equilibrium result here. If we take the field to 0, this becomes the linear transport coefficient. Okay. So we've gone from trying to develop a relationship for determining the direction of a process for a system away from equilibrium. I think it's getting late. And getting the fluctuation theorems. Then looking at how that translates into a dissipation theorem, which will then give us the linear transport coefficients through a non-equilibrium route. Okay, so just finally, just a recent result that we have is that this relationship can be applied locally or as well as globally. And so it provides a relationship for the local transport coefficients. And we've done some work recently looking at local diffusion coefficients. There's many different expressions for local diffusion coefficients, but this provides a way of using statistical mechanics and non-equilibrium molecular dynamics arguments in order to get the diffusion coefficients in a system which is inhomogeneous. And so we looked at a system where we imposed a density profile and calculated the diffusion coefficients in different regions of that system. As you can see here, we have a system. This is a unit cell of this periodic system. And we've got regions of low density and high density. This is dividing this cell up into bins and looking at the diffusion coefficient in each of these. These are the integrals of time correlations for the different bins. L1 is at the edge where the density is low, and we determine a diffusion coefficient by looking at the long time limit of this curve. And you can see that it is a little lower, but similar to a homogeneous system of the same density. So these are 3 results for 3 systems which don't have a density profile at different densities. So the higher one is 0.38 and the lowest points on the graph are at a density of 0.87. And not only do the limiting values, are they similar, but the shapes of the correlation functions are similar as well. And I also note that they're not exactly the same, partly because the bins are finite, and so there's a range of densities across the bins, but also because when you derive the local diffusion coefficient, there's coupling between what's happening locally, this L, the velocity in the local region, and the velocity of that particle time later when it's no longer in that region. Okay, so then just in summary, hopefully you can see that, if you didn't already realize, that simulation modeling of non-equilibrium systems is a really powerful way to study systems at scales that are inaccessible, there's a word missing here, experimentally. So we can look at systems on the small scale easily. We can't look at system on the large scale easily, but experimentally it's the reverse in many cases. We can find lots of information when the simple models don't exist. One point that I wanted to make is that, after a very long history of developments in theory and algorithms for simulating homogeneous shear flow, we're at a situation, at a point where we can start to be applying them to very complicated systems. And the reasons why we can do this is that the algorithms exist, but they've existed for a long time in some cases. Periodic boundary conditions commensurate with the flow and ways of implementing them are relatively new in some cases, but they've also been incorporated into readily available software. And so you can start to look at complicated systems which would take too long to simulate with usual in-house code. It's also at a point where there's improvements in the efficiency of the code that can be made to look at and to develop, to adapt for the new computer architectures. I just gave a little bit of theory. Some of it is relatively old now, but some newer, to show how the equilibrium systems, or at least a class of equilibrium systems, are amenable to being able to be put on a more sound theoretical ground. And this allows us to then explain their behavior, but also provide useful relationships which might make studying them easier, or understanding equilibrium systems easier as well. Okay, so thanks again for everybody for your participation in this event. And I acknowledge the people again, and I've just highlighted my group members that had contributed to the work I presented today in Europe. I was going to highlight the people here, but actually they were all involved in some way, so I didn't do that. So thanks very much.
Thank you, Deborah. Thank you very, very much for this really nice talk, which is now open for questions. We have already Luigi Delle Site, who is booked to ask his first question. Luigi, if you want, you can unmute and ask the question directly. There might be a problem with that, so let me read the question for him. Oh, okay, apparently there is a problem with that, so I'll read the question for him. If possible, could you comment on how your theoretical approach relates to a theory of reference, such as the Bergman-Lebowitz theory of non-irreversible processes?
I think there's a lot of connection, actually. So this is a very clear answer. So there are lots of different approaches for considering this. Our approach is to start with a system which is at equilibrium and then evolves towards a steady state. And I think that is slightly different, if I understand correctly, from other approaches, which tend to focus on the steady state themselves.
Okay. So unfortunately, Luigi doesn't seem to be able to interact with you to continue this conversation. Maybe while we wait either for his technical problem to be solved or for other questions that I invite the audience to ask, just let us know that you want to do so by typing that you want to do that on the Q&A session, and then we can relay you. We can invite you to unmute, and then you can ask directly. Let me ask a question that I had since the very beginning of your talk, because you mentioned that you were going to discuss deterministic dynamics. Mm-hmm. And I was just wondering, because it sounds like a lot of the things that you are discussing could be generalized also to the case of stochastic dynamics. And so I have two questions. First, is that impression true? Can you also, adapt these theories to the case of, say, Langevin or whatever? And then the second question is, do you have a preference for deterministic dynamics for some reason?
Yeah, okay. Yeah, no, good question. So yes, you can adapt it to stochastic systems, and we have we have in some cases. And so there's different ways of doing that, is to, one, take the deterministic dynamics that we have and add a noise. So one situation that we looked at was, rather than have a field which was constant, have a field which had stochastic noise added to it. So in that case, it's very straightforward, and the result you end up with is pretty much the same if the noise is not correlated. So if we've just got white noise. So you end up really basically with the same result. The other case is, yeah, you could use some Langevin dynamics. And in that case, it's a similar approach, easier in some ways and more complex in other ways. In that case, you can get more than one dissipation function, if you like to call it that. And that's because you can consider it from different frames of reference. So, for example, looking at the one system where the system that we looked at was a particle which was being pulled along in a bath. And we could look at a function which would obey a fluctuation relation, if you like, from the position of the particle in the lab frame or relative to the trap. And you end up with two different results in that case, two different functions which satisfy a fluctuation relationship. They're both related, but they're different. So that is a slight difference. We can also look at some systems with some correlated noise, and in that case, the fluctuation relations do vary. So yeah, so you can look at the theory for systems which are stochastic and use similar approaches. As far as my preference or my for deterministic systems, I guess when we use stochastic terms, we're using it to represent the surroundings, which we can't describe deterministically. It's how I feel that we're doing it. So if we had a particle being pulled along in the bath, we can model all the bath molecules, if you like, in the simulation, and to treat them deterministically rather than treating them as a stochastic effect on the trajectory that we're looking at. It does make it many more degrees of freedom, but it also avoids having to make approximations for what type of stochastic system you have. You have the deterministic system, there's no choices, it's just as it is. It might be more complicated to model, but that's why I do think that looking at things through a deterministic eye can be quite useful sometimes.
Gotcha. Okay. I guess I was thinking more in terms of thermostating with deterministic thermostats where we know.
Okay. Yeah. Okay. So a lot of that was kind of related, associated with that, in that if we wanted to treat these systems theoretically, it's sometimes easier to treat it theoretically if we treat it deterministically. Certainly with thermostats, if all the thermostats in some way are fictitious, because we even if we put them in the walls and treat the system, they're fictitious. So there is no strong physical reason, I guess, for treating it deterministically rather than stochastically. But certainly as far as the derivations, having a system which is completely reversible, having a system which is completely deterministic does make sometimes the theoretical treatment easier.
Okay, thank you, Deborah. We have Mike Allen online who should now ask his question.
Okay.
Hello, Mike.
You could have given this talk much.
Thank you for a lovely talk. With molecular dynamics, of course, there's always one extra step. There's an algorithm for implementing the discretized versions of the equations of motion. Now, a lot of effort has been expended on doing that for Hamiltonian systems. But for all of these equations with extra terms, is that an issue that people have looked at in detail, just making sure that the discretized forms of the equations don't introduce some pathological features that screw everything up?
Yeah, I think, well, we have to take into account that it is discretized and that hopefully it doesn't mess everything up. But they're chaotic systems, and if our time step is small enough, we argue that it should be representative of what's happening. I mean, for testing the relationships, the theoretical relationships, we tend to use a fourth order Runge-Kutta integrator, because you don't have something like a symplectic integrator, which we would use in equilibrium. We did a little bit of work on an iterative integrator, which ensured that we had some of the properties completely conserved. But in the end, the results we tend to get that we've been looking at haven't caused problems. Yeah, and I don't know how much research is being done now. There was a period where there was quite a bit being looked into, and I think it's just assumed that if you test that, use a smaller time step. Runge-Kutta is important for these when we're applying the field. So self-starting doesn't depend on what was happening the previous step. And that was actually more important than, I guess, the symplectic nature of some of the algorithms that we're using.
Okay, thanks.
Yeah.
Thank you. So we have one question from Anya, who seems to have problems with camera and microphone, so I will read it for you. And that is, could you comment on the abbreviation SLOD?
Oh, yeah. Yes, this was introduced quite a long time ago. And I mean, I'm just relaying a story, and actually Bill Hoover and Carol Hoover have recently written a new book where they talk a little bit about this. But there were two algorithms which were used, and I guess the original one was an algorithm which was derivable from a Hamiltonian, which is called the Doll's Hamiltonian, the Doll's equations of motion and the Doll's Hamiltonian. And where we had in the equations that you saw, we had a Q with the gradient of the velocity and a P of the gradient of the velocity. In it's very complicated. So, okay. So there's the Q and the P, and there's a Kewpie doll. So I don't know in Europe if you have Kewpie dolls, but I think in America, they have these little dolls that they sell at fairs, which are Kewpie dolls. And so because of the Q and the P in the equations of motion, it became the Doll's algorithm. in the slot algorithm, the Q and the P are swapped around. So the Doll's algorithm became the slot algorithm because it's Doll's written backwards, basically, because the Q and the P were swapped around. Yeah, so that's my interpretation of the stories that I've been told in that. But there's a little picture of the QP Doll in the new book that Bill and Carol Hoover have written.
Yeah, that's the same story that I had heard, Deborah. So thank you for reminding us about it. Any more questions from the audience? Okay, if not, well, thanks again for accepting to do this with us. And, you know, particularly appreciated given the time of day in your
I'm
part.
sorry, I was getting a little tired just saying this. I'm waking now. So I'll look forward to hearing the other talks.
I think no issues from our side. So thank you again. Thank you very, very much. And I think we're now ready to move to the next talk, which is going to be presented by Benjamin Sorkin from Tel Aviv University, who is going to discuss for us universal relations between entropy and kinetics.
Okay, do you hear me? Do you see the screens?
Everything seems to be working fine. Thank you.
Great, excellent. So thank you very much. It is a great pleasure to present my work in this event. My name is Benjamin. I'm a PhD student in chemistry from Tel Aviv University. These are my PhD advisors, Professor Chaim Diamant and Professor Gil Ariel. Together, we're working on entropy and entropy production estimations in non-equilibrium systems. And today, I'm going to show you a general inequality relation between entropy and kinetics. So the possibility of having such relation is in some sense a surprise. Usually thermodynamic quantities such as temperature, internal energy, heat capacity, they're considered unconnected to transport coefficients. These thermodynamic quantities are usually have to do with material steady state properties and with the equation of state. They just require the units of energy and length. While when you go out to equilibrium, when quantities such as temperature, pressure might be ill-defined and others too complicated to compute, people often resort to computing transport coefficients instead to characterize their materials, coefficients such as diffusion coefficients, viscosity, and conductivity that just tell you at which rates transport of particles, momentum, and energy occur. Now, as you can see, these quantities have completely different units. They also require the units of time, and they have to do with the dynamic properties of your system. Nevertheless, there were quite a few approximations and phenomenological theories that were proposed to connect these two categories. Let me mention just two of them. A rather famous example of such relations is the Adam-Gibbs relation. It is a kinetic theory for glass forming liquids. It connects the relaxation time of that liquid with the entropy per particle of configurations, where A is some phenomenological parameter, tau 0 is a reference, relaxation time, and T is the temperature. It gave rise to some other very important glassy theories. Another less famous relation is the Rosenfeld relation. It relates the diffusion coefficient of the material's constituents. Then it is rescaled by these factors. It's just what you expect from like simple Boltzmann kinetic theory, ideal gas computation. And it relates this reduced diffusion coefficient with the entropy per particle of your material. You subtract the ideal gas entropy per particle for the particular thermodynamic parameters you have, and A and B are some phenomenological numbers. B is usually between half and 1. It was practically some educated guess. It seemed to have worked for the ideal gas of hard spheres, and it was speculated to work for other fluids. Some different scaling was proposed by Zugutov a bit later, and there's a very good review by Dyer that I really recommend to read. It is a phenological relation, as I said. In Rosenfeld words, it is a semi-empirical universal corresponding state relationship, so it might fail, and it does fail for complex systems. What I'm going to derive with you today is a universal and exact relation. It is somewhat similar to the Rosenfeld relation. These 3 dots, I'm going to tell you exactly what they are. You notice these inequality compared to the equality you had before. And under some assumptions, you can get the Rosenfeld relation as well, but our relation is not restricted to just liquids. And most importantly, and in light of today's event, it is valid out of equilibrium. Okay, so now I'm going to show you the derivation, and then I hope that I will have time to apply it for a rather curious system. Okay, so now I'm going to derive the relation, and for that purpose, as any statistical mechanical calculation requires, we assume an ensemble of n identical and indistinguishable particles, which constitute some material, this beaker of water. The configurations I denote by X, and all of this stock is going to be within steady state, no dynamics whatsoever. I'm characterizing these in general non-equilibrium steady state that my material occupies. And the main trick for this derivation is that I am always going to compare my indistinguishable picture with an hypothetical, completely distinguishable picture where I track every single individual particle within my ensemble. Just as an example, if I denote the microstate distribution in the distinguishable case as P of X, just what is the chance to find the red particle here, the blue whatever particle here, and the rest with the rest of the particles. In order to find the microstate distribution for the indistinguishable case, I denote by P tilde. To relate them, I just need to sum over all possible permutations in this case, and since the particles are all identical, it gives me this n factorial factor. An important thing, since we are going to relate dynamics with entropy, because of Gibbs paradox and the super extensivity, if you don't include the n factorial factor, the thermodynamic entropy is going to be related to the indistinguishable distribution. So that is the definition I'm going to use later. Okay, so I'm looking at some discretized sequence of snapshots. And the short time scales over here, I have some microscopic dynamics at play, for example, the Liouville equation or something like that. What I assume, it is my first assumption in this derivation, is that I have some finite relaxation time, I denote by tau, past which my system, the indistinguishable system, converges to steady state. Perhaps equilibrium if it has one, or to a non-equilibrium steady state. For the purpose of this derivation, I will not discretize time with delta t goes to 0 to really solve how my dynamics look like. Instead, I'm going to take delta t to be much bigger than tau. So this kind of allows the time discretization. And the path is going to be a series of snapshots that are separated by this delta t much bigger than tau, and I denote these series of snapshots by xk. Great, so let us begin from the indistinguishable picture. Since my configurations are separated by delta t, my indistinguishable particles would converge to the steady state distribution at every single snapshot. My particles have mixed, they collapse to this steady state. It means that the path distribution, that is the joint probability to obtain this snapshot, then this snapshot, etc., separates into a product of independent probabilities, which again, P tilde is the steady state microstate distribution in the indistinguishable picture. On the other hand, when I look at the second decomposition at the distinguishable case, I follow every single particle. I look at the, for example, diffusion process that this red particle undergoes. And so while my indistinguishable particles just underwent mixing, my distinguishable particles are tagged and tracked, and they will undergo this particular process. And so, since I've waited for very long times, I assume that some memory effects and stuff like that are wiped out. So my second assumption is that I have Markov jumps from one configuration to the other, and that it is the system's translation variant. In other words, that when I look at the joint probability distribution to obtain this path, it has this propagator, this W here, which tells me the probability distribution to jump from x0, this thing, to x1, this one, during time delta t. And because of the translation variance, I'm going to take them as it only depends on the difference. Great. Now I want to relate the two pictures. In order to relate the distinguishable picture to the indistinguishable one, as usual, we just need to sum over all possible permutations at every single time step. Now, this is a terrible monster, which we are not going to be able to carry out completely. We notice that the first sum just has to do with scrambling which particle underwent which trajectory. That is, if I am going to scramble these particles and replace them downhill, the probability is going to be the same. And so I get n factorial from this first sum. But then later, if I have already committed that this particle has begun here, the probability that it would jump here is much different than where I am to permute its identity with this particle and it would have to jump here. The distribution is very different. And so I'm not going to have the same, say, 10 to the 23 permutations factorial that I'm getting from here, but just some finite sphere of neighbors with whom I have some likelihood to exchange paths. So since during this finite, intensive delta t, I'm only having some finite number of particles with whom I exchange positions, a thing I want to do is just to drop these permutations. Since probability is a non-negative quantity, I know for a fact that when I drop these permutations, I underestimate my probability. Since I don't include all paths, once I permute them in the distinguishable picture, my indistinguishable distribution for the paths is underestimated. Great, so this is the first inequality. Now that I have some relation between the indistinguishable picture and the distinguishable one, this has the propagator in it with all the information on the dynamics. This has just the steady state distribution in it. I compute what I call the information content of the path distribution, just the p log p of that distribution here to obtain some path of distinguishable states. And once I compute it with the Markov decomposition, and the other time I use this relation and use the independent decomposition. And then I get this relation. It is the first rigorous relation I have for you today relating entropy and dynamics. This is the many particle propagator. The problem is that this thing here, I mean, were I to ask an experimentalist in the audience to track 10 to the 23 particles, I'm going to be yelled at. So I'm going to make this bound a bit more applicable. We're going to make another simplification. I'm going to trace just one particle. Were the particles independent, say an ideal gas, this many particle propagator would just separate into a product of independent single particle propagators, which I denote by W. Because in general, my particles do not move independently in the general material, I know just from information theory that I have this inequality here. So this inequality came from the fact that I just dropped the permutations in my paths. Here, I do some simplifications. I only track one particle. So this is another more applicable relation between entropy and kinetics. I've said diffusions a few times this talk. So in many systems, a tracer particle would just undergo diffusion and it would obey this propagator, just a Gaussian usual thing you expect from Brownian motion. The mean square displacement grows linearly with time with some late time diffusion coefficient. Once you put it in the previous relation I showed you before, we get this, the central result that I have for you today, which relates the late time diffusion coefficient of your tracer particle, the relaxation time of your system, the time it takes for your independent particles to really mix and converge to steady state, the entropy per particle of the material, these just dimensions, and A is some reference constant. Entropy is defined up to a constant. You must choose your zero entropy reference. It is not just limited to usual Brownian motion. Let me show you slight generalization. I will now consider anomalous diffusion. So the mean square displacement will grow like time to some power. A rather general propagator I can write in Fourier space looks like this. It comes from the generalized central limit theorem. Once again, I go back to real space, insert it into the relation between entropy and single particle propagator, and I get this somewhat more general result when here you have the late time anomalous diffusion coefficient, that F here, and the relaxation time is just to the power alpha, the anomalous diffusion. Great. So to conclude, we get inequality relations between thermodynamic entropy, and today I'm showing you the relations to diffusion coefficients. A is, again, some reference you should determine from zero entropy reference. And equality happens for two cases. I need them to come both together. I must have paths that do not mix, so the undercounting I did before is not severe. And I need my particles to move in an uncorrelated fashion, such that the many particle propagator would separate into single particle propagators. I only have time for one example, so let me show you the most unusual system we could think of. Consider the case of one-dimensional single-file diffusion. The particles do not interact. They just move with a bare diffusion coefficient d0. They have some diameter. They occupy some line fraction. However, they cannot pass each other. Once these meet, they just collide and move apart. Because they cannot pass each other, there are quite serious many-body effects. It's well documented in the literature. For example, you get an exponent half subdiffusion instead of having regular diffusion where they phantom particles. Now, why is this system interesting for our cause? Because the 17th particle from the left will always remain the 17th particle from the left. That is, I don't have any permutations in my trajectories. So one of the sources of the inequalities is automatically resolved. I only have one possible source of inequality, and that is the correlated motion between particles. Okay, the entropy is very simple to estimate. I have the line fraction, and so the entropy is just the log of the available volume for my system. The only relaxation effect in here is collisions between particles. I can estimate from the typical distance between them and the bare diffusion coefficient. I put it inside our relation, and we give a prediction for the anomalous diffusion coefficient for the system, and it completely agrees with what you find in the literature. So it's even not an inequality, it's equality. And we think that it has to do with the fact that the particles don't really interact directly. They move freely within the boundary conditions that the neighboring particles apply on them. And so the second source of inequality is not that severe either. It's speculation. With that in mind, we tackle a problem with no analytical solution. That is, I apply to the same problem before, just taking point particles for simpler calculations. I'm adding an external periodic potential. It has no, there is no analytical prediction for the late time anomalous diffusion coefficient. The amplitude of the potential is E. It is periodic with some lambda. The entropy, again, is very simple to estimate. Just from the Boltzmann factor, you get the minus log of the density plus some Bessel functions of E I didn't write here. We perform Brownian dynamic simulations from which we find the anomalous diffusion coefficient F. Tau, the relaxation time, we estimate rather naively. We say that it comes from the crossover from the normal diffusion, that is before the particles collide with the neighbors, to the anomalous diffusion regime, once they have collided sufficiently many times and they now subdiffuse. In terms of the density dependence, we see again that there's a complete equality between the exponent of twice the entropy, which what we need, and the transport coefficients that we must put. But when I go to the energy dependence, we see that there is no equality. We begin to miss a bit here. What's annoying is the fact that the inequality is in the opposite direction. I want these points to be above the entropy, as you can see here. And the reason for that is very simple. Tau, we estimated just from collisions. It's the crossover from normal diffusion to anomalous diffusion, while there's a very important Cramer's escape rate problem here. The particles should overcome a potential which is 1.5 kT. So since we underestimated tau, we can use this inequality to give some prediction what is the correct tau. For the system, it should bring these points at least above this line. Okay, so I went a bit above time, so let me summarize very quickly. For translation variant systems with finite relaxation times and Markov propagator, we find rigorously that it is possible to relate thermodynamics with kinetics. Any situation appropriate propagator can be inserted in either of these relations, and you obtain a relation between entropy and the suitable transport coefficient. These relations hold out of equilibrium. I never assumed equilibrium at any stage, and they are valid for any degree of freedom so long as these assumptions are satisfied. Specifically, we give a rigorous relation between diffusion coefficients and entropy per particle. The equality is obtained for systems with non-passing trajectories, where the permutations I didn't take into account don't play a role, and when particles are uncorrelated, so the single and many particle propagator bear the same information. Something I didn't quite have the time to elaborate today is that when you take into account that there's some sphere of neighbors within the permutations that I didn't take into account so far, is if its size is proportional to the typical correlation size in your system, you get a relation which is somewhat similar to the phenomenological Rosenfeld relation, which somewhat corrects it by putting some inequality or something like that. I can elaborate it in the poster session. And in terms of future works, most importantly, we hope to verify these relations. The Rosenfeld relation did require realization time, but once putting it, we hope that things will start working again. Since particle permutations were so important for the derivation, we wonder how will it generalize for multi-component systems, for polyelectrolytic solutions, for polymers, subassembly, etc. And lastly, we want to take viscosity, heat conductivity, and other transport coefficients into account. It would require some adjustments since these are not particle properties, but rather field properties. You need the momentum field or the thermal energy field. Great, so that's all I had for you today, and thank you for your attention.
Thank you, Benjamin, for this interesting talk, which is now open for questions from the audience. So if any of you wants to ask one, just let me know in the Q&A session. You have mentioned two hypotheses, right? Markovianity and time translation and translation invariance. I was just wondering which would be the more painful to remove, or if you want, in other words, yeah.
Okay, so the translation invariance, we thought of it, for example, where you look at diffusion around the surface of a material, something like that, since the structure there is somewhat different. I'm guessing how diffusion the diffusion coefficient changes the closer you get to the boundary. It would be important. And in that case, you would like to break the translation invariance just in one axis. So we hope that it won't break completely the derivation apart. The Markovianity is essential. If I don't have Markovianity, I would not be able to relate the entropy with just a propagator to jump from some distance. I'm guessing if it's, say, have some memory to 2 steps before, it will involve some double integral of distances, something like that. But it would require a lot of modifications in the non-Markovian case. So yeah.
Okay, good. So we may just move on for time reasons. So thank you again, Benjamin, and let's go to the next talk, which is by Pasquale Di Gregorio, active turbulence and topological defects in nematic liquid crystals.
Thank you very much. Hello, everybody. It's very nice to participate in this workshop. Let me share my screen. Okay. Okay, I hope everything works. So yeah, today I'm going to talk about active turbulence and topological defects in nematic liquid crystal. First of all, what we mean by active systems are those types of systems where single constituents are able to extract energy from the environment or from internal reservoir to produce work. So they are out of equilibrium systems, but let me say there are a special class of out of equilibrium system because as compared to the kind of out of equilibrium system that we heard about in the previous talks. Because like the reason why they are out of equilibrium is not related to the fact that there are like external driving, but the mechanism that drives the system out of equilibrium takes place at the level of the single constituents. And it's very common to see, to find this kind of features in system that are alive. So, for example, if we look at birds, they transform again energy into motion, and they are able to self-organize, and they use these properties to form flocks and move together during migration. Self-propulsion, it's also a very fundamental feature for synthetic active systems like self-propelled particles, and for example, these systems are able to form clusters and they do that in absence of attractions between particles. Going to, let's say, smaller scales, bacteria, this is E. coli bacteria. Bacteria are motile as well, and they use flagella to move around and look for food. And also motility and self-organization are also very fundamental properties in the interior of a cell, as you can see here. I mean, and this is the kind of system I would like to try to focus on today. So if you look at the interior of a cell, as you can see here, you can see a very dense network of paths. And these paths are microtubules that the cell is able to arrange and continually create and rearrange in its interior, and it uses the paths as let's say trays to move things around its interiors, to move substances. This is a very nice animation of how it works. So we have these microtubules and we have these proteins, which are called kinesins. They attach to the microtubules and they walk on them, and they carry stuff around the cytoplasm of a cell. So we would like to understand a bit better how this works. And what we can do experiments. There is this very nice experiment which has been around for almost 10 years. So these people have been able to isolate these microtubules and put a lot of them together like this motor protein, these kinesins. In this case, kinesins have binding edges on both sides, so they can bind to two different microtubules. And as soon as they bind to the microtubules, they start walking on it. So as a result, we have like a macroscopic stress in the system, which pushes microtubules one relative to each other, as you can see here. So what happens if we put a lot of them together? This is what happens. If we have a lot of these microtubules and kinesin motors, we have a very complex dynamics. We have a chaotic dynamics, and we see patterns. We see patterns that, and the typical size of these patterns is very much it's larger than the typical size of the molecule. This is this kind of dynamics quite closely resembles something that we already know, which is turbulence. And this is the reason why we call this this kind of dynamics active turbulence. And I will try to give you like I'll try to show you how to build like a model to study this kind of systems and how to get like a fundamental properties, fundamental feature of this very complex dynamics. So first of all, as we deal with this elongated molecules, the kind of systems we will ground the description of our system on a very well-known class of material, which are a pneumatic liquid crystal. The fundamental properties of pneumatic liquid crystal is that they exist in two different states. We have a high temperature state where the system is disordered, and a low temperature state where the position of the molecule is not ordered, but all the molecules they more or less point in the same direction. This transition to the pneumatic state is already let's say incorporated in the classical phenomenological theory, which is called Q-tensor theory of pneumatic liquid crystal. So we have the equation of motion for the Q-tensor. The Q-tensor is the mathematical object that we use to describe this kind of systems where the molecules, they have an elongated shape, but they don't have an head and a tail. And the dynamics of Q is governed by this phenomenological Landau free energy. Landau-Dejean free energy, and the form of this free energy is responsible for the fact that if we let the system evolve at equilibrium, at low enough temperature, it will relax to a state where, again, the molecules point more or less in the same direction. Okay, then we have the equation for the velocity field, because these molecules are embedded in a fluid. And this quite closely resembles Navier-Stokes equation, but differently from the Navier-Stokes equation, we have in the stress like a coupling with the nematic field. And also, since we want the system to be active, since we want to take into account the presence of this local stress, we have to add extra term that, as you can see, it's proportional to the local nematic field, and this means that the stress is always directed along the direction of the local orientation of the material. And this is, again, as I told you before, this gives us the idea of how what is driving the system out of equilibrium, and in this case is not an external stress, but it's really a microscopic stress, which is somehow related with the local properties of the system. Another important things about nematic liquid crystals is that they have topological defects. Topological defects are regions in the system where something goes wrong, let me say, and like here and here, and we're not able to define in this point and this point, which is the direction of the nematic field. These two are the kinds of topological defects that we have in the nematic liquid crystal. Plus a half defects of this comet-like shape. Minus a half defects of this triangular shape. And in a passive system, these two defects tend to attract to each other and eventually to annihilate between each other. So as I told you before, if we let the system relax at equilibrium, and we have defects, these defects they will annihilate between each other, and the system will relax towards another state. But let's see what happens at topological defects. Now you remember the kind of dynamics that we have in the active system, and we see here what happens to the topological defects. Now topological defects, it's true that they annihilate between each other, but they are also created in pairs. And so what happens is that at some point the system relaxes to a state where the number of defects is constant. And also you might notice that if we look at the defects, they will give us, if we look at the location of defects, they will give us a quite clear idea of the underlying chaotic dynamics that we have. Okay, so we have considered so far 2D systems. The next question is, the question now is what happens in 3D? Because, and this is quite a natural question, because we started from a system which is the cytoplasm of a cell, which is a 3D system. So we want to study this kind of system in 3D. As we move from 2D to 3D, everything changes as far as topological defects are concerned. First of all, because we don't have point-like defects anymore, but we have defect lines. And as you can see here in this experimental picture of 3D nematic liquid crystal, defects are arranged into lines, and the lines, and as for 2D, if we let the system relax, the lines will coarsen, will get straight, will combine between each other, and the system will eventually relax towards more or less ordered state. Now again, we are the TVT, and we start from a system with no defects. And at some point, as you can see, the system starts to create defects. And this is related to the presence of this microscopic stress. And the defects grow, and they continuously combine between each other, and they reach like a stationary state with more or less like a constant defect density. Okay, so we look at the defect density, and we look at a slightly different quantity, which is this lambda d. Lambda d is the average defect separation, which is of course related to the defect density, because the system is, the configuration of defects is more or less homogeneous. It's very interesting to notice that this quantity depends on activity. And in particular, it depends on this length scale, active length scale, LA. LA is defined as the square root of the ratio between K and alpha. K is the coefficient in front of the elastic free energy. Alpha is the coefficient of the active stress. And it depends linearly on LA. So this is telling us that activity introduces a new length scale in the system. And this length scale can be related to the average defect separation. So we have a tool looking at defects to recognize this new length scale in the system. We can look at the probability density function of the defect length, and we observe that this probability density function has a peak, and that the location of the peak depends again on the activity. And it scales, as you can see here, linearly with this active length. So active lengths not only control the average separation between defects, but also the average length of the defects. We can do something more detailed, and we can look at single defect loops. And we look at this radius of gyration. Radius of gyration is an average radius of the defect line. So it gives us information not only on the length of the defect lines, but also on the how the line is arranged into space. So what we see here, and if we plot the radius of gyration as a function of the defect length, we recognize two families of defects. So the small defects, like very short defects, they populate this region of the plot where the radius of gyration depends linearly on the length of defects, and this means that small defects have like a planar shape. They are very rounded and regular objects, while very long defects, for very long defects, the radius of the gyration scales as the square root of the defect length, and this is a typical features of random walks. And in fact, if you look at the configuration of these long defects, you notice that they have this tangled structure. Among this very tangled long defects, so now our numerical simulation, they are we have periodic boundary conditions. This means that the system is periodic along the three-axis. So among all these long defect structures, we have closed defects, but we also have open lines. And the interesting thing is that if we look at the length of these lines and how this length depends on activity, we see two different behaviors. So if we look at closed loops, as we've seen before, as the activities increase, the length decreases, and their number increases. But if we look at these open lines, these lines that wraps around the system along any of the three directions, and we increase activity, these lines get longer and longer, while the number is always of order 1, and it does not depend on activity. Okay, so wrapping up, what we've seen is that the kind of dynamics that we see in a system of pneumatic liquid crystal with in the presence of a microscopic axis stress is a turbulent-like dynamics. And what we also seen is that the certain topological defects in this kind of system gives us a very powerful tool, I will say, to recognize the main features of the system, the typical length that we have, and how they depend on activity. This is all, and thank you for your attention.
Thank you, Pasquale, for this very, very nice talk. So while we wait for questions from online participants, please just let me know in the Q&A session if you want to ask one. I was just curious to hear a bit more about the numerical methods that you're using to simulate this system.
Yes. Let me go back to the model. So we simulate this model here. So we have two equations coupled, one for the Q tensor, one for the fluid velocity. So we use as a method to simulate this system a so-called lattice Boltzmann methods. So this means that the equation for the fluid velocity is it's actually like a high. It's called a hybrid lattice Boltzmann because the equation for the fluid velocity is integrated through this lattice Boltzmann method, which basically is a method that uses a discretized version of the Boltzmann equation to solve to integrate the dynamic of the fluid. And the dynamic for Q is solved by like a finite difference method. So we use this method together to integrate our couple equation of motion for Q and U.
Okay, and so the finite difference method implies the existence of a grid different than the one that you use for the lattice Boltzmann, or you get away with a simple.
Sorry, I didn't understand.
I was just curious about, because now you're sort of mixing two different solution methods. I was just wondering if there may be incompatibilities between the two, but probably not. You just get away with the same.
No. It's yeah. It's just like you have to take care of the couplings, but
That's okay. All right. Well, I don't see any other questions from the audience. And if that is confirmed, I think this is the perfect time to thank again all our speakers, Pasquale, Benjamin, and Deborah, for taking the time to prepare such nice presentations for today's session. And also thank you, all the participants online, for being with us.